This is a crystal of calcium tungstate. It is being pulled from the melt as it grows. This type of crystal, prepared with a small amount of neodymium as an impurity, was used in the first continuously operating solid-state optical maser. The optical maser is a radically new device which represents a significant step forward in our ability to generate light in a controlled way. An optical maser is an optical oscillator, in many ways similar to a radio oscillator, except that it gives out light instead of radio waves. It can be used to generate a beam of light which is at the same time very powerful and highly coherent. Coherent means, very roughly, well organized. We'll see what it means more precisely later. First, let's take a look at these 5 gas masers, which show the achievement of optical maser action in the noble gases. They are helium, neon, argon, krypton, and xenon. Although these gases fluoresce in color, all produce maser beams which are in the infrared. This optical maser uses a ruby crystal instead of a gas. It gives out an enormously powerful burst of maser light in the red, which lasts about 1,000th of a second. To show you how powerful is the burst of maser light, I have arranged a lens so as to focus the beam on a graphite block. I shall count down from 3 and fire on 0. 3, 2, 1. What you saw just then was a white-hot burst of hot gas leaving the block from the point at which the focused maser beam hit the sample. Let's try it again, now that you know what to look for. 3, 2, 1. Here is the graphite block after several flashes of the pulsed ruby maser. I said at the beginning that an optical maser is an optical oscillator, which is like a radio oscillator, except that it gives out light instead of radio waves. As I'm sure you know, radio waves and light are the same in kind. They are both electromagnetic waves. They differ only in frequency and wavelength. The frequency at which the optical maser oscillates is around 10 to 30,000 times higher than that of any previous generator. The optical maser in fact generates light, but it does so in a way very different from sources with which we have previously been familiar. Here are some familiar light sources. All of them give white light or something reasonably close to it. White light may be thought of as composed of all frequencies between the lowest, which the eye can see, at the red end of the spectrum, to the highest, at the blue. With a modern prism spectrometer like this one, white light is directed through a prism, which splits the light into its component colors. This spectrometer also enables us to see a single color. We'll place a card here in order to display the spectrum. A second card goes back here to display the single color which is passed through a slit between the cards. As we darken the room, the spectrum becomes quite visible on the front card. When the front card is removed, the single color, red in this case, is passed through the slit to the rear card. When I move the spectrum across the slit, I can select any color I please. In this way, I can use the spectrometer to pick out a restricted range of frequencies. You will notice that I said just now not frequency, but range of frequencies. In fact, at the moment, the band of frequencies coming out of the spectrometer amounts to perhaps 20 trillion cycles per second, or, in radio language, 20 million megacycles. And that's quite a frequency band. I can narrow this band by narrowing the entrance and exit slits of the instrument, maybe to 1 million megacycles, which is about the best I can do with this particular instrument. But, as you will see, by the time I have narrowed the slits to get as near as I can to a single frequency, there is hardly any light left. And this is a chronic fact of life. As long as we use white light sources plus some sort of filter, which is what a spectrometer is, the nearest we can approach to a single frequency is still a band which is very gross by radio standards. And even this can only be done at the expense of having very little power left. Over here, I have a laboratory sodium lamp. When we shine light from this lamp through the spectrometer, we find that it consists, as near as this experiment can tell, of just one band of frequencies in the yellow. Actually, an instrument of higher resolving power will show that there is not one line, but two, each line being some tens of thousands of megacycles wide. So we do better with this lamp than we do with a white light and a filter, but for many purposes it still isn't good enough. What we would like, both for scientific and communications needs, is this: a source of light of, as nearly as possible, just one frequency, which radiates that light in, as nearly as possible, just one direction. This is what the optical maser does. In order to explain how the optical maser works, it will be well for us to look a little more closely at conventional light sources in order to see how they differ from radio transmitters. Here we have a diagram of a Hertzian dipole, representing, for example, a simple half-wave antenna connected to a radio oscillator. You can see lines of force and the way in which they move in time as the dipole radiates energy. The dipole is oscillating at a perfectly definite frequency. Because the wavelength of light is so much smaller than that of radio waves, a half-wave antenna tuned to light frequencies would be inconveniently small, even if we knew how to excite it. Fortunately, however, the atoms in a hot body or in a gas discharge themselves behave like tiny Hertzian dipoles. In such a source, each dipole radiates independently of all the others, and each at a different frequency. I'm sorry that we haven't been able to include the moving lines of force in this picture, but, as you can imagine, it will be quite a job. And that's just the point. The radiation coming out of this block will be a confused jumble, more or less uniform in intensity in all directions and with no particularly well-defined frequency. What we have is a noise generator. Look now at what happens in a sodium lamp. Here, too, the atoms behave like little Hertzian dipoles, but now they all radiate at much more nearly the same frequency. But, as you will see, there is no particular correlation between the instants of time at which the light attached to each miniature Hertzian dipole flashes out. We can describe this lack of correlation. Suppose we put a clock next to the dipoles. Then we pick a dipole and notice what time it flashes. As the hand swings, it indicates when the other dipoles flash. As number 5 flashes, number 1 is nearly ready to flash again. The total time elapsed is one period of the oscillation. Now we can quote by what fraction of the period each of the other dipoles is late. This quantity we call the phase, which can be quoted in fractions of a period, or in radians, or in degrees. The point about the sodium lamp is now that the phases are random. There is no correlation of phase between one dipole and the next. The expression we use to describe this situation is that there is no phase coherence in the atomic system. I think you can now see that what we need in order to obtain a proper optical oscillator is precisely phase coherence. This is just what happens in an optical maser. The trick, of course, is to set the phases right. What we need is a system set up in such a way that, as the light wave you are generating travels along, the phases of the atomic Hertzian dipoles are so arranged that they always help the wave grow. Now let's see how it's done. Let me start with an acoustic analogy. The analogy isn't quite exact. Analogies seldom are, but it will help us to get started. Here we have two tuning forks. Let's leave one aside for the moment and look at the vibrations of the other under this microscope. the microscope, we see the top surface of one of the tines. The filing marks on the tine are quite bold and will serve as a good reference to observe the amount of amplitude. As I strike the tuning fork, the tines start moving and sound is radiated. The amplitude clearly starts at a maximum and then decays as the sound gets weaker. One reason the amplitude decays is that the energy the tuning fork has while it's vibrating is being converted into sound. The fork is all by itself at this stage and emits energy for no other reason than that it has energy to emit. Let me call this process spontaneous emission. Now we're ready for the next step. The second fork is brought up very close to the first. I'm going to start the second fork into vibration, and I want you to watch what happens through the microscope. You can see the amplitude of the fork build up. This means that energy is being taken up by the first fork from the radiated energy of the second. This process I shall call absorption. Now let's see what happens when the second fork is struck while the first is already vibrating. You will have noticed that sometimes the amplitude builds up when the second fork is struck, and sometimes it dies away rapidly instead. This is because the instant at which the second fork is struck relative to the vibration of the first is entirely a matter of chance. That is, the phases are uncorrelated. In those cases where the amplitude builds up, we again speak of absorption of energy by the first fork. Where the amplitude dies away fast instead, clearly the second fork is compelling the first to radiate its energy faster than it would if left to itself. This process we call stimulated emission. Now let's go back to the atomic Hertzian dipole. Now, of course, the sound field is replaced by the electromagnetic or light field. Exactly the same three processes can occur. If the atom is not excited, it can absorb energy from the light field. If it is excited, it can emit energy into the light field. And the same distinction can be made between spontaneous and stimulated emission. If the atom is all by itself, it can emit spontaneously. But it can also be stimulated to emit faster than that if there is light of the right frequency present. But the analogy must not be pushed too far. A tuning fork can be given any amount of energy we please, and its phase is exactly measurable. Atoms, on the other hand, in stationary states, can only be in one of a discrete number of well-defined energy levels. And if you know definitely that an atom is in one of these energy levels, you will not be able to find out anything about its phase. So, do not expect to find an easy analogy to the step in the acoustic experiment in which we changed from absorption to stimulated emission by changing the relative phases of the two forks. Unlike a tuning fork, if an atom is definitely in the upper of two energy levels, it can only emit, and stimulated emission will occur regardless of the phase of the incoming light. In the process of absorption, an atom is pictured as moving upwards from a lower to a higher level of energy. Similarly, in emission, whether spontaneous or stimulated, the atom moves down as it loses energy to the radiation field. The only difference between spontaneous and stimulated emission is that in stimulated emission, we hasten the transition by forcing it with the same frequency as that which the atom is prepared to emit. Furthermore, suppose we have just one atom and one photon. If the atom is in its lower state, there is a certain probability of an absorption occurring. If in its upper state, a certain probability of a stimulated emission. Now, the point is that these two probabilities are the same. Thus, if we have a large number of atoms, and there are more of them in the lower than in the upper state, the system will, on balance, absorb energy from the light wave. If, on the other hand, there are more in the upper state than in the lower, the system will, on balance, give off energy to the light wave, which, in consequence, will grow. When there are more atoms in the upper than in the lower state, we say that the system is in a state of negative temperature. Such a state can only exist if we have some way of driving atoms up into the upper state by some outside source. This is not always possible, but in some systems we can do just that. The process of generating a negative temperature, that is, the process of selectively exciting more atoms into the upper state than there are in the lower, we call pumping. The fact that a light wave passing through a negative temperature medium will grow enables one to make an optical oscillator. Here's how it's done. We have a collection of atoms driven in some way so as to be in a state of negative temperature. This collection of atoms is placed between two parallel mirrors. I can best explain what is expected to happen as a bootstrap operation. Suppose that you start a plane wave having the correct frequency moving between the mirrors. As the wave moves forward, it causes stimulated emission to occur and consequently grows in amplitude. When it hits the mirror, it bounces back. Since no mirror is perfectly reflecting, it will lose some amplitude in the process. Some of the energy lost stays in the mirror. If the mirror is thin enough, some gets through. On the return trip, the amplitude builds up again as more stimulated emission occurs. If there is little or no gain from stimulated emission, the wave will die away after several reflections. The break-even point occurs when the stimulated emission gain just makes up for the losses at the ends. If this break-even point is exceeded, the result will be that the wave should continue to build up forever, or rather, until it has exhausted our ability to maintain enough atoms in the state from which stimulated emission occurs. A sort of photon chain reaction, rather like the neutron chain reaction which happens in an atomic bomb. A few moments ago, I described what happens as a bootstrap operation. This was because I had to ask you to consider that a plane wave was present at the beginning in order to get the thing started. Actually, of course, so long as you are past the break-even point, you don't need to introduce an external plane wave at all. This is because, sooner or later, as a result of fluctuations in the field, there will be something like a tiny plane wave present, and as soon as such a fluctuation occurs, the plane wave will keep on growing to the exhaustion point. So, to make an optical maser, you need three things. First, you need a cavity. A means for keeping the light bouncing to and fro, or, in the language of electronics, to introduce feedback. A pair of flat, parallel mirrors constitutes one type of cavity. Second, you need a medium. A collection of atoms capable of giving gain through stimulated emission at some frequency. These atoms must possess some suitable pair of energy levels between which transitions can occur with the absorption or emission of light of the desired frequency. Third, in order that stimulated emission shall dominate over absorption, you need a pump. In effect, a means for driving the system into a state of negative temperature. Here is the helium-neon optical maser. The two mirrors are in the box-like ends. The medium has as its active part the gas neon. In fact, you can see the tube glowing pink, just as a neon sign does. Pumping is done by including helium along with neon in the maser tube and exciting the mixture by coupling to a radio frequency generator. The generator excites the helium atoms and puts them into a long-lived excited state. Collisions with neon atoms then occur, and a negative temperature is set up in the neon. The signal given out by this maser is in the infrared, at a frequency about 30% lower than the lowest you can see. The beam of this maser can be seen directly by using an image converter tube. This tube has a tiny television screen on which the beam of the maser produces a green spot. The beam is extremely parallel and has a divergence of less than a minute of arc. This is smaller than the eye can resolve. The reason for this, of course, is that only light traveling to and fro between the ends, very close to the axis of the structure, stays in the cavity long enough to join in the oscillations. Thus we see that a cavity with flat ends generates plane waves, or something very close to it, and these waves escape through the ends as a parallel beam. Here we have another experiment which demonstrates the purity of frequency of the signal given out by the helium-neon maser. What we are doing is beating together two different output frequencies from the maser, just as you can do with two radio frequency sources. The two oscillating frequencies fall on the detector, which mixes them together and generates the difference or beat frequency. The beat is displayed on this frequency analyzer. Here is another version of the helium-neon maser, which I can use to illustrate some other features of the device. This one gives out a beam of visible light instead of infrared. The principal difference between the two lies in the frequency which the end mirrors are made to reflect. Because the beam is visible, you can in fact follow it right through the apparatus and out the ends. Notice that this time we get on the screen a pattern more complicated than just a simple spot. From the pattern, we can deduce in what mode of the cavity the maser has been excited. Now I want to talk about a different sort of optical maser. This one uses a solid. The medium here is a crystal of calcium tungstate neodymium. Such crystals are made in the way you saw at the start. The cavity is just like the one used for the gas maser, except that instead of having separate detached mirrors, we make the ends of the crystal very flat and very parallel and cover them with a reflecting coating. One big difference between this and the helium-neon maser is the pump. This is the pump for the neodymium maser. It is a small but powerful mercury lamp which floods the crystal with white light and sets up the condition of negative temperature. This elliptical mirror focuses the light from the lamp on the crystal. The top is a flat mirror and fits over the housing when the apparatus is working, as it is here. The beam given out is in the infrared, and an oscilloscope can be used to demonstrate the existence of oscillations. The lower trace shows the pumping light, and the upper trace the maser signal. This is another solid-state optical maser. It gives out light that you can see. The apparatus is rather different from the one you just saw. The pumping lamp is here, and its light is reflected off this parabolic mirror and focused on the crystal. The crystal is ruby and is positioned inside a dewar. The light given out by this maser is red. Here is the maser beam as it is directed into our camera. The 1 degree reference gives you some idea how slight is the divergence of the beam. The ruby crystal itself is cut in the shape of a trumpet to make maximum use of the light which is focused on the end of the crystal. The reason for this is that you need a much higher pumping intensity to make ruby oscillate. Historically, the first optical maser ever made generated pulses of maser light rather than a continuous signal. We are still very much interested in such devices because, although the signal doesn't last very long, it's much more powerful while it's on than anything we can get out of a continuous maser. Here is a pulsed ruby maser, which will show you what I mean. Instead of a continuously running lamp, we have a flash tube, shown here with the ruby crystal. It produces a flash lasting only 1,000th of a second, but hundreds of times brighter while it's on than even the brightest continuous lamp. The ruby crystal is placed inside the spiral, and the whole assembly looks like this when mounted in a housing. The lamp is flashed by discharging a bank of condensers through it. To look at the maser beam, I have inserted a glass tube filled with smoke between the maser and a card. Remember, the beam is only visible for about 1,000th of a second, so I will count down from 3. 3, 2, 1. We'll go in a little closer and do it again. 3, 2, 1. It's of course impossible to give you much idea of how bright the spot really is. In the continuous ruby optical maser, the power in the beam was about 10 milliwatts. In that flash, the peak beam power was about 10 kilowatts, or around 1,000,000 times as much. And there are tricks we can use to get the power 1,000 times higher still, which is to say 10 megawatts, provided we are content with a flash duration of a few tenths of a millionth of a second. These powers may sound impressive, and they are. With them, scientists have been able, for the first time, to make 2 photons coalesce to give 1 of twice the frequency, to make ultraviolet light out of red. It isn't a very efficient process, maybe only a part per million, but with ordinary light intensities, you can't detect it at all. This experiment is only one of a number which have been made possible by the high light intensities generated by the ruby optical maser. At sufficiently high light intensities, the optical properties of many materials are quite peculiar, and we're going to have quite a time finding out why. We have in the optical maser an entirely new scientific tool with which many new kinds of experiment will be possible. On the one hand, with continuous optical masers, we are now able to carry over all of the standard radio and microwave techniques, such as the beating experiment which you saw, to the optical frequency range. On the other hand, the fantastic light powers made possible with pulsed optical masers enable us to see new optical effects, as in the doubling up experiment. And each new scientific discovery will be examined for its technological implications.